So today's topic, demolition case studies, not case studies that are complex to write. These are ones that we're discussing today, which are some great projects which are in really tricky locations or have a very difficult scope. So if we take a step back and think about how this all starts, its basic form and demolition is the act of taking a structure apart, whether that's full or partial. And there are two key ways of demolition. There's deliberate collapse or progressive. Deliberate collapse often covers the high profile wow factor type jobs that you see, the blow downs and the pull downs, whereas the progressive demolition, that can cover both full and partial demolition depending on the structure, whether it's going to be refurbished or totally removed. And then typical methodologies for progressive demolition includes top-down demolition, where the structure is removed floor by floor with small excavators operating on the working floor. A high reach is where a large excavator with a long reach arm uses the arm to kind of demolish the structure progressively. Dismantling, this covers debuilding the structure, often in the reverse order of how it was built, but not always. It's very common also to have a combination of all these methods. So for example, a structure that may be demolished top down to a certain level and then high reached once it gets to a certain level, it may be dismantled in a steel frame. So here we've got typically what the layman thinks demolition is, and this is typical for demolition works like 60s and 70s, and includes the progressive demolition of the structure using a wrecking ball. It's quite impressive. Essentially pushing the structure or damaging the structure to induce a collapse, as you can see here, which is just happening. And yes, it's quite quick, but it's very difficult to predict when it's going to go, and uncontrolled. And a lot has changed since then. So in reality, in the UK, we find that there's well-developed high-tech industry for demolition in the UK. So here we've got at the top left, we've got Birmingham New Street Station. This is a specially developed excavator where Coleman and Company worked with JCB to develop a bespoke machine to enable them to demolish these beams as part of the upper retail level demolition. Bottom left, centre point, which is the complex demolition of the 33 floor structure, but this is just to cut and carve 33 floors up. So this is right at the top of the tower. In the middle there, we've got DSM's large demolition machine, and that's sat on a working platform. And I think this is still the largest in the UK, weighing over 200 tons. It reaches about 70 meters and can run quite a large attachment at that height. This is multi-million £multi-million investment plant we're talking about here, but it does come very handy when we're trying to demolish structures safely. And then on the right there is specialist lifting gear for various operations. But what makes a demolition project complex can generally be split into two categories, I suppose. So we've got location or environment, such as where the building is, whether it's next to something sensitive like a network rail boundary. So that's one side, where it is, location. And then the other side is the demolition scope. So for example, a full demolition of a 5-story structure may be quite simple if it's in the middle of nowhere or there's nothing on the boundaries. But then if we're changing that scope to cutting parts out or demolishing floors whilst keeping the facade and elements such as this, it will make the same job much more complicated, involving more input from structural engineers and temporary works detailing, etc. And also, this is quite akin to the implementation risk, which was defined in BS 5975 2019, and this execution risk, which I've put at the bottom there. So that's the combination of implementation risk, and that's the combination of execution risk and consequence of failure, which is the location and constraints, and the execution being the competency of the contractors and difficulty of the task at hand. For more details on this, I'll push you towards our previous webinars where we've discussed the temporary works flowchart for 5975 and checking temporary works and the temporary works procedures webinars that we've done. But you'll see our YouTube channel for the full set of those where it discusses that in more detail. So now we're all kitted out with the basics of how a project becomes complex. Let's take a look at some examples. So first, we've selected quite a variety of different projects that kind of showcase how things can change depending on the scope of work, and this is today's agenda. So I'll hand you over to Dave for our first one. So over to you, Dave. I'll just stop sharing now.
No worries, this is going to be smooth as we expected. So the first case study that we're going to talk about is Keynsham. So this is a site in Bristol where we were looking to demolish both a water tower and a chimney that were next to each other. And to spice up this job, this is a bit of an overview of the site. They were quite close to the network rail boundary, and a number of other structures that were to be maintained. So we've got the chimney to the south, the water tower just above it, and the only free space to really do the pull down is kind of towards the network rail boundary and towards the southeast of the site. So what we were asked to do was to provide a safe method of bringing these structures to ground. So we were looking at the temporary stability during pre-weakening, looking at the cutting sequences to allow these structures to be brought down, look at the exclusion zones, which were quite complicated because of the network rail boundary, and then calculating the pull down force to actually enable the structure to be pulled down. So first, we'll have a look at the basics. So when you are looking at pulling down a structure or pre-weakening a structure, you need to have a think about what are the imposed loads on that structure. Luckily, with both of these with the chimney at least, we had some archive drawings. With the water tower, there were no archive drawings, and we had to carry out a survey ourselves on site to calculate the weight of the structure. You then have to consider both the notional load due to that self-weight or any kind of out of plumbness of the structure, along with the wind loadings during the demolition. And then the final thing that everyone always forgets about is to make sure it comes down. So look at how much force you require to then destabilize the structure following your pre-weakening. I've just pulled a couple of things out of BS 6187, which is the kind of code of practice for demolition. It goes through a bit on your exclusion zones, how large they need to be, what your drop zone is, and that kind of area, and a bit on designing collapse mechanisms. So we are trying to create instability that can then be initiated. So if we look at the chimney first, which is the more simple of the two. So what we're trying to do here is reduce the moment capacity of the chimney in one direction, so that we make sure that the chimney falls in the direction we're looking at. And this you can see from the cut sequence on the right, that we are looking to pull the chimney to the right-hand side. We create a bird's mouth cut in that side, and then we progressively cut the back side of it and shim it. That shimming makes sure that the chimney can't actually fall to the left. It maintains that compressive capacity. But when you do try to pull it over, you don't have the tension capacity, so it does weaken the structure significantly. The other bonus of this kind of method is that the final cuts are made from the back side of the chimney, which designs out the risk to the operative carrying out that burning if there's any kind of inconsistency or an unknown in the chimney that causes a collapse prematurely. The operative doing that work is in a position of relative safety compared to on the other side of the chimney. So that's what we're looking at there. Moving on a bit, well, that's a drawing. So this is the final section here, is to look at where our exclusion zone was, and what we did to mitigate the risk to the network rail boundary is that we initiated the collapse using a high reach excavator from behind to push it over, and we used another large excavator with a tether on it to ensure that the full radius could not kind of pass over the network rail boundary. Made sure the chimney fell in the direction we were looking to pull it over or push it over in. So you can see there, everything's clearly marked out with the direction the chimney should be going and the risks involved. The water tower was a bit more complicated. So we've got kind of a truss structure with 3 levels with a lot of water tank panels on the top. As you can see there, the note was to make sure that the water tank is definitely empty prior to the pull down, as that would affect the self-weight of the structure. So we were looking to design a mechanism here to allow that structure to be pulled over from a safe distance. And we had to maintain sufficient stability under notional and wind loading to prevent collapse prematurely. To do that, we ensured that there was kind of controls in place on the wind speed prior to the cutting works. So they picked a couple of days with a good weather window to ensure they could get all of the pre-weakening done and complete the pull down in good weather without excess wind speeds. And that makes the process a lot safer. So the cuts you could use. So I'm just going to go through a few types of cuts just for the people who may not be familiar with demolition, just to go through the benefits of each type of cut and the drawbacks on what they actually do. So firstly, you get a castle cut. So, and this one also has both a shim and a hinge on it. This prevents or allows shear force to be transmitted through the connection, but obviously a very limited moment capacity or a moment capacity in one direction where you've got the shims, so it can't fall over towards the left. But in this situation, when a force is initiated, you would get it to fall over towards the right. And this is what we did on the back legs of the chimney, as I'll show you in a bit. And this is also a type of hinge cut. You also get a sloping cut. So this enables the actual force, which is coming from left to right in the situation, to pull this leg out and to initiate the collapse. And this is done in stages with shims inserted to maintain capacity, but this cannot really transmit any shear beyond the frictional force from the vertical load, which is why it's important to know the vertical load on each section. And finally, a flat cut, and this was used on the bracing elements, where you leave a small amount of tabs left in place to maintain stability in the temporary condition, but which can be broken by the pull down force. And that finally creates the actual mechanism. We provide a sequence of cutting here to make sure that as before with the chimney, that the last cuts are made from a position of safety. So cut number 1 is just a flat cut with shims. Cut number 3 is that sloping cut, and that's where the pull down force is initiated. You make cuts on the bracing with the tabs left in, which are then broken by the pull down force. And finally, you've got a hinge at cut 4. The other advantage of this cut sequence is that the point of rotation when this does come over is around 0.4, which limits the collapse radius, which was very important given the adjacent network rail boundary and how far away the excavator could be positioned to actually initiate this pull down. That brings us on to Gladstone docks, which I believe Josh is going to go through. Josh, you're muted if you're talking.
No, after 2.5 years of Zoom practice, you think I would have learned that by now. Thanks, Dave. That's great. Thank you. So now on to Gladstone docks in Liverpool, and that included the demolition of various heavy plant used to transfer coal from ships in the docks to land-based transport. It was a complex demolition project due to its location within a busy dock that was still operational, and you can see that in the background of those photos. And it was also quite complicated due to the scope of work that was required. There were very large structures that were no longer operational, therefore we couldn't use their inbuilt control systems to move them to safer configurations or positions, and everything we had to do or move was carried out manually with other cranes or excavators. Also, the information that we had on the structures was helpful for overall geometry and things like that, but the details were lacking in a number of places, a number of critical places, unfortunately. So taking accurate weights was quite a challenge. The plant was to be demolished was a coal stacker, a coal reclaimer, and 2 coal unloaders, which I've highlighted there. So also in the foreground, you can see that to the side there was a natural gas plant there, which was highly flammable and was quite a very sensitive asset, which was a key driver to the demolition methodology that we went with on a lot of these. So first, let's take the reclaimer demolition, and here it is in all its glory. And it had a series of buckets on a wheel at the end that and then on one end, and that's what kind of when you've got the stockpile of coal, and that's what kind of reclaimed the coal, and then it kind of spat it out down that conveyor onto a conveyor system, and it had a counterweight on the other side, which was then left in position. And oh, sorry, I've realised that there's a video on here that I can't play that Dave can play. Dave, could you pinch the
Yeah, I'm ready for it when it comes to
okay,
it.
sound
I'll swap over.
Apologies, folks. I'm having some technical issues this morning. So it was left in position. Therefore, we towed it along the tracks to position away from that natural gas tent and carried out the controlled drop of the booms. And this was engineering by balancing the loads and laying loose fill down at each drop point, so we could ensure that as it came down, it was come down evenly. And then the next slide, i.e. Dave, that's when you can see the video, which is the drop-in action. So take it away, Dave.
Can you stop sharing? I'll throw mine up.
And if you could keep yours up, and then I'll carry on from there.
Hopefully you can see that.
So what we've got here is we've got someone in a point of safety above, and what they're doing is they cut the block in the middle, and then the two halves kind of drop down. But once this is dropped onto the ground, then it could be processed in a much safer manner from ground level with large excavators. The philosophy behind it, there it goes there. So it drops down, and that means that that can be processed from the ground level there now. And yes, it's high risk. Dropping a structure like this is controlled, but it's only so much control you can put on that. But it's over a short period of time when the site exclusion zone can be in place. So the overall risk is lower to alternative methods, which would include either extended hours working at height or unstable structure left for an extended period. So that was that is the reclaimer. And now onto the coal stacker. This one could be nibbled from one end with a high reach excavator. The complexity here was that the boom was supported at regular points on the tension ties that were coming off from one end, and at critical points the ties would no longer provide that support, and we would have that unstable cantilever if we weren't careful. Also, the tracks ended here for this piece of plant, so we couldn't tow it down away from that sensitive third-party asset on the boundary. So the solution here was the careful demolition, removing specific elements in sequence to ensure that we maintain stability. So that's the coal stacker. And finally, now onto the coal unloaders. These were very large key cranes right on the edge of the dock. It was dismantled with a 1,000-ton crane and some smaller mobile cranes, and it was very a careful operation because we didn't want to drop any of those elements into the dock. But the flat photo of me, that was right at the top there, and just kind of shows how tall that structure was. The cranes weren't operational. We did have lots of information on the mechanical and the electrical workings of it, which was all great to see, but what we needed was the actual structural details, the thicknesses of flanges and webs, and how the structure was constructed, which we key parts of that information was missing, and that was really important to enable us to calculate accuracy for the mobile crane operations. So next slide, please, Dave. And the challenge there was we wanted to balance out what the factor of safety that we'd increase our estimates by, because we couldn't be too sure. It involved me clambering over all the steel work with my ultrasonic thickness gauge to figure out how thick the box beams and things were. So what was helpful though was that we had a carbon copy for each because there were two identical structures next to each other. So once we dismantled the first one, we could use that information to verify our weights for the next one. Next slide, please, Dave. The structures were essentially dismantled top down until they were totally removed, and you can see some photos there. So that's that massive 1,000-ton crane there being used to just dismantle the structure working top down. And we had, in a few lifts, we had a tandem crane lift. So it's really important to mitigate risk of overloading those cranes when I was working out the where the center of gravity would be. So that was the key challenge, and that's what made this a complex demolition project. That's it from me on the Gladstone docks. Over to Richard for Premier House.
Yeah, I'll just get this share going. Hopefully that was smooth. Hopefully that worked. It's been a while since I've been allowed into these presentations, so I don't want to ruin this one. But today I'll be talking about Premier House, where we were the demolition engineers for PP O'Connor. The job was a complex cut and carve job to start with, but then with the phasing and wanting to retain different aspects of the building, and the fact that it was in a busy city centre, that's the middle of Manchester there, and next to a river, and next to Victoria Bridge, which is a listed building, all added a little bit of complexity to the job. In time, the whole structure is going to be renovated and rebuilt, but I'll just be talking about the north section, the bit highlighted in red and orange there. These were going to be completely demolished as part of the works. That area that's highlighted is it's got a 2 to 3 story basement car park in it, and we wanted to remove this, and this was going to be the main headache for most of the works that we were doing. The existing basement was a retaining wall for the Deansgate Road, which was also right next to the site, which was a busy main road, and Victoria Bridge to the north, and that bridge is going to crop up a few times in this talk. But during the works, part of both the roads were still in use. The hoarding line did take out 1 lane of traffic, but 1 lane of traffic was still live throughout these works. And as you can imagine, there were several elements of temporary works required to get this demolition on the go. So first, some basic acro propping to allow some small plant to operate on the top levels of the building. For the 8-ton plants, we needed a bit more back propping than the 5-ton, so that's where the complexity starts. Keep it going, the back propping got a little bit more extensive. Let's say when we got down to the ground level, they wanted to use a 80 to 90-ton high reach excavator down here. So when we were back propping this, it had to be a lot more extensive and extend all the way to the bottom of the basement slab. Fortunately, at the bottom of the basement slab, we had bedrock, or just about. So all the forces from this could be nicely put into bedrock and not require huge foundations to be put in, as well as everything else. But as you see, the back propping goes right the way down and goes right the way across the building for where that big excavator is working. But the real headache of this job was the retaining wall at Deansgate Road. The road had an open lane, and on the lane that was closed, we possibly had that 90-ton excavator tracking about to get on and off the slab where it was reinforced to take that load. But the part of the structure, the plan was to keep part of the structure in place and keep the retaining wall propped while using part of that substructure, and to keep it shored that way. This was developed with the project team so that we could keep this in place throughout the works. But as you can see from the pictures I've left up here, these are historic pictures from the 70s, I think it was, and it shows that when they built their original retaining wall, there was large buttress walls in place and what looks like very minimal temporary works when they built it. But unfortunately, we were unable to gather any information on this wall because it was behind another retaining wall. And there was always the chance that when they were doing subsequent works to the building, that all these buttresses had been removed or different aspects had been removed. We just weren't sure. And so to get all this work safely done, we had to assume that most of these bits were removed. But because we did know that this retaining wall was there, it did mean that some of our designs could be later. But the information that we could get from site from old pictures like this means that we could save time and lots of money in this propping system that we eventually got going, which you can see the start of in the bottom left, bottom right there even. But this is the design that we ended up with, a few megashore props raking down throughout the building, just holding up that retaining wall on the left there. And that was on every column line and on every level as well, just to make sure that the road wasn't affected by any of these works that we had going on. And then just from that, you can see how much of the building we left in place. It wasn't much. It was one bay that we kept in place. And you can just see the size of those mega shores at the bottom there, with a little bit of the cut line propping in as well. That was just simple. We just had that in place. Now, because we were next to so many different sensitive things and roads and everything else, the river and the grade 2 listed bridge, we had lots of monitoring in place. So you can see all the different types of monitoring we had going on there. The first type was just movement monitoring to make sure that our props were doing the right thing and retaining that wall properly. But of course, you can't just take monitoring points and just go, oh yes, it moves a bit. You need some baseline monitoring to see what was going on beforehand. So that was the second type of monitoring we had to put in place. Then we had more monitoring for, there we go, more monitoring for Victoria Bridge itself. We had to have very sensitive deads on them to make sure that it didn't move and that we wouldn't harm a very nice looking listed building. And then the fourth type of monitoring was my favorite, because it was specified by the Canal and River Trust and I didn't have to do any calculations for it. That's the way I like things to happen, just them telling us what to do. And lastly, we had no slide for it apparently, because I didn't add it in. We had more monitoring for vibration. There was lots of services running right across site, right across towards the river edge, and we had to make sure that the vibration from the demolition works wouldn't affect any of these services. And as you can imagine, there was a lot of the demolition works going on here. They're in the green arrow type down here, the vibration monitoring points. So we had vibration in Deansgate Road, or at Deansgate Road, and at the bridge as well. And I hope that was complicated enough, because it looked complicated enough, it felt complicated enough, it took me ages, but that about sums up the work we did. And that's when they were just getting finished. And that is the cut line propping there, which was just holding up where we did the final cut, and that's where the end of our work stopped on this phase. And then that's it looking pretty when the handover happened for the final fluid temporary works. Okay, and I think that's me. I don't know who I'm going back to, but let's say it's Josh. So
It is.
There you go, Josh.
It is. Thank you, Richard. Thanks. That's great. Okay, so now onto our final case study, and this is a bit of a throwback Friday, or keeping in the theme of throwback Friday, because it's not quite throwback Thursday. But thank you, Richard. And what I'm going to talk about this time is Centrepoint Tower, which is a kind of a cut and carve demolition project. On the right is a photo that I took on an early morning walk to site, and you can see how exposed it is, and the little room that we've got around it right in the city of London, and lots of constraints around that job. So let's take a look at this one. We carried out the temporary work design services on behalf of the demolition contractor, who was John F. Hunt, and this was a £3 million grade 2 listed Centrepoint complex redevelopment project. To realise this redevelopment, all the structures undergoing significant alterations, which required extensive temporary works, and it covered 3 main areas. So we've got the Centrepoint Tower, which I've shown in red there on that plan. We've got Centrepoint House, which is shown in blue. And then we've also got the basement of the tower and the house, and then a pub, which is down the bottom. So the basement kind of extended and joined all 3 structures there. And the principal temporary works included structural assessments on the global stability of the structure throughout the demolition. This work was critical at both the top of the tower and in Centrepoint House as well, considering the significant demolition works on the levels 32 to 35, which was the roof, and then the 6 floors of the residential housing above Centrepoint House demolition works. The demolition was carried out using the robotic Brock excavators with hammer and muncher attachments, which was used for the majority of the demolition works due to the quite complex and the quite complex nature of that demolition scope. We designed the propping and to facilitate the demolition of key structural elements until the installation of the permanent works. We designed false work for pouring upper floors in the tower, and that included justifying those back propping loads onto the existing structure. We had basement propping designs and retaining wall analysis. Most of the designs that we carried out were category 2 check risk category, and therefore we carried out the required checks as well. But are all also included inspecting and signing off some of the more complex temporary work schemes, and we worked hand in hand with the John F. Hunt, the demolition contractor, to ensure that our designs, due to their complex nature, were installed correctly, and we were happy with them as designers, because I was the lead designer and also temporary work supervisor for the job. So let's cut straight to the most high profile part of the job, high being the operative word here, because we're going to look at the tower. So this is the top of the tower, and removing almost all of the floors in the top 3 levels, half of the roof as well, and a continuous strip spanning from one end to the other on level 32. So we were removing a significant amount of the structure up here, and hence a significant amount of temporary works was required to realize this, and a 3D sequence as well, just to make sure we could have that control on. It was very clear how we were communicating our proposals to the contractor. You can see the extent of the demolition here. The facade was retained as shown in the photo, so from the outside it looked like we weren't doing much at all, but in fact there was a lot going on inside, and this is what the effort was for. So that's a view over the London from one of the double-storey penthouse suites that would be been constructed at the top of the tower. The 3 areas of the support were required to realise the demolition at the top here. So the centre in the top levels, end of the top levels around the lift cores, and also that strip along level 32, which was removed. A key element of the top of the tower package was the global stability assessment for the top of the tower, and the design of numerous sway bracing schemes and propping schemes that's ensued. And these stability frames were made out of the proprietary RMD kit, Super Slims, and they were located between several shear walls and lift walls and columns, and you can see the design of those here. So these are the drawings that we put together, showing how each frame was constructed and where they were positioned. And then this is a lovely photo of the RMD stability frames in the center of the structure. At that point, 2 of the floors have been removed, and you can see there that there's a floor in the bottom still in place that would also be removed. So you're looking at quite like a few stories of just open air structure that used to hold the boilers and boiler tanks and water tanks that served the tower, but now those were changing to mains pressure, so they could turn these into lovely penthouse suites. Here's another picture there. You can see we were keeping these shear walls in place for the permanent works proposal, and they were required for stability purposes of the top of the tower. So here you can see that is with the floor about to be poured at level 33. So that there's a false work deck that you can see there. So there's another story of fresh air under that. On the right hand side, you can see a facade retention scheme, which was wasn't designed by us. That was installed prior to this creating this air void in the center of the top of the tower. And you can also see there that the roof has been removed in the center. So we were keeping these structures together and stable. In the corners at the cores, we had other stability frames which kept the shear walls and the cores all in the right position that we needed them to be into, and that's one of those stability frames there. So once those stability frames were installed progressively as we kind of came down, it was very important that we had a meticulous control over the demolition methodology, because if you look at all that red, that's all the floors that are coming out. So to ensure that this demolition sequence was controlled, we produced 3D drawings showing element by element exactly what's going to be carried out. And this stability and justification that we did all relied on the sequence of demolition being balanced and carried out in our proposed sequence. And that was controlled by those 3D drawings that we put together, which were quite extensive, but it was impressive to see the 3D drawings that I had in my hand when I was doing my regular inspections, and seeing that actually realized on site was really great to see. So now if we drop down a little bit lower to those floors that we can see those photos on, we're going to come down to level 32. And this frame structure was designed to effectively prevent the structure from parting in the middle, because the proposal was to remove this deeper spine beam and replace it with a post-tensioned beam, so that the ceiling of level, the underside of level 32 was just a nice flat ceiling for this penthouse suite. So during the demolition process, we did come across some cracks as well, which you can see. Yeah, so that's the temporary works that are being installed there. And this is that hole that you can see. I'm just going to shoot now to a photo there. So you can see at the tops of where we were installing these frames, we spotted some cracks, and these were monitored, but no further movement was found. And it was essential that the propping was very tight, and that tightness was checked at the beginning, during, and the end of each shift, and movement was monitored with spot checks on total stations and those telltales there. But that was a kind of movement monitoring, such as Richard was talking about, really important to make sure that we, in theory, understand the structure and how it's going to behave. And so we need to make sure that monitoring the structure to make sure that it is behaving how we believe it's going to be working. And here we've got the construction of that post-tension slab at the top there. And then there we've got the finished product. Somewhat an anticlimax of just a grey slab there, but that was the end of lots of site effort, design effort, Cat 3 checks from external parties, and ended up with some new floors and some swanky new penthouse suites. But that heavy plant structure is no longer there, and we've got 2 levels of open plan space. The new levels were constructed in October 2016, going a little while back now, and making the temporary works redundant, and therefore proving the success of the scheme. So that's been our Throwback Friday case study of the Centrepoint Tower development from a temporary work standpoint. So hopefully today, the projects that we've highlighted and run through, they illustrate to me certainly how important it is to get the correct methodology in the first place, which is absolutely critical for the complex demolition projects. The right methodology changes from job to job and client to client, which is why some good trusted relationships between the project team lead to good projects, good in this case meaning safe, successful projects that are delivered on time. We work with many of our clients early on, even at tender stage, to provide that engineering input, which assists in choosing the right method and the right temporary work solutions for your complex demolition project. So that brings us to an end of our presentation today, but there's certainly not the end of education on the subject. There's lots of information out there from well, we've got the Temporary Works Forum listed there. There's a wealth of knowledge on there. There's also a few documents which I've listed here. So we've got the Temporary Works Principles, which is an ICE publication. We've got Temporary Works Toolkits articles, which is produced by the iStruct. We've got the NFDC guidance, which was revised, I think, in 2019. That's a guidance note on temporary works, and also the Safe by Design, early focus on constructability in temporary works. All these documents can help you de-risk a complex demolition project by enabling you to make the right decisions at the right time. As we know, knowledge is power. If you've got that knowledge and that base knowledge of when to spot difficulties coming on further down the line, and you can plan ahead, then it's going to make for a much smoother project. So I'll hand over to Christian and we'll have our question time, our Q&A. So if you have got any questions in mind following on from our presentation today, then drop them in the Q&A bar at the bottom,